I want to talk a bit about what the security working group does, why it exists, and how OPC UA users can benefit from it. The reason it was originally created, the primary reason, was to be kind of a rapid response team for dealing with the vulnerabilities. We recognize that vulnerabilities happen. Some of them are going to affect the specification, and we needed to have people available, security experts from many of our different vendors, um, to sort of sit down and be able to address the issues that have come up. And so we've developed a process that we've applied numerous times over the last couple of years, um, in terms of de determining if specification changes are needed, notifying different vendors on with instructions on how to fix issues, and then publishing the security bulletin, and then providing those CVs to organizations such as MITRE and US CERT, so it can get as disseminated as widely as possible. The second aspect of the work has to do with developing new security-related features. And so I'll be talking a bit about some of the work that we've been doing and some of the progress that we've been making on some of these different features. Now, when it comes to the security bulletins, all of the security bulletins that we have produced over the last couple of years are all published on the OPC Foundation website at the link provided. If you would like to receive a mail whenever we release a new one, then you can subscribe to the Google group, which is listed there. And so we haven't had a huge number, but they do come up, and they have required changes to stacks and vendors to update their stuff. The most recent one came out of the 0-day initiative, Pwn to Own contest they had down in Miami. For the first year, this year, they had a special category for ICS systems, where hackers were offered prize money to find exploits in different industrial software products. And 2 OPC UA stacks were put on the target list. And we were very happy to find that, at least from my discussions there, that the hackers sort of looked at the stacks and looked at and tried to break into them, and found that it was a pretty hard target. So they tended to move on to other targets, which offered an easier path to getting their money. The ANSI C stack, which they tested, which was commercial ANSI C stack, had no they would not find any exploits in. The .NET open source code base had a denial of service attack crash they were able to replicate. That has been fixed, and the CV has been published. In terms of the new capabilities, the big thing coming out this year is ECC. Elliptic Curve Cryptography makes it a lot easier to implement on small devices, particularly as ever-increasing security requirements keep requiring that the bit lengths for keys get larger and larger and larger. The release is in its final stage, sort of posted on the website for people to comment on. The release is expected in Q3 2020. Couple things that ECC adds into the picture. It's sort of worth noting that these features aren't something that was needed for ECC. It was a case of, as time has gone on, we wanted OPC UA to adapt and sort of continue to improve its security posture over time, and we identified some additional security features that weren't in the original original specifications that we've incorporated into the ECC profiles, specifically authenticated encryption and this algorithm called Cha-Cha Poly, which is extremely efficient software-only algorithm. It doesn't necessarily require hardware acceleration, so we've got high hopes for it in terms of being a good basis for embedded system development. And the other thing, which is a consequence of the Heartbleed exploit that came out a few years back, was having perfect forward security. And now we can say that OPC UA has profiles that offer you perfect forward security because the ECC mechanisms use Diffie-Hellman and key negotiation. Now, the ECC security profiles. Now, in UA, all of our we create a bunch of a relatively small number of canned security profiles to maximize interoperability. So you don't need to worry about all the details of the different algorithms and which ones are used in combination with which. You'll basically have a short menu of different profiles that could be used, and you simply pick which ones you want to take advantage of. Things got a little bit more complicated for ECC because of all these different curve families, and there was no one-size-fits-all curve family. The NIST is the workhorse, widely used, needed for U.S. government, but its association with NIST has unfortunately meant that there are people out there who simply don't want to use them. The brain pool curves are an option, but they're relatively slow. And the last ones are the ones that, again, we have the highest hopes for. It's the Edwards curves, which includes curve 2. They're also called Bernstein curve, 25519. And our hope is that this will become effectively the default policy. There's a bit of challenges in the short term because the libraries don't necessarily have the support that we would like them to have, but that's a problem we believe is going to resolve itself as OpenSSL and these other crypto libraries release updated versions in the next few years. The next project that we're spending a lot of time on is related to device provisioning. One of the visions that we've had for the OPC UA specification is we want to make sure that security doesn't become so cumbersome that it simply gets turned off by owner operators. So we're constantly looking for ways to identify the pain points and add specifications in to facilitate or help owner operators manage their security for their systems. And for the longest time, we've had Part 12, which includes a certificate manager that does a lot of the certificate related functions. And device provisioning sort of takes that effort and extends it out over the life cycle of the device, and with the intent of being able to completely automate the installation of a new device. So you take a device out, you plug it into the network, and it just automatically configures itself. Now there's a lot of stuff in the background that has to happen, and the device provisioning spec is defining the APIs and the architecture that will allow this to happen. Now, one of the things that we did as part of this effort is come up with a device lifecycle that's appropriate for industrial automation. A lot of people are looking at this. The device lifecycles are a lot of people are doing work in sort of with the IoT devices, and a lot of the devices that we're talking about will be IoT devices of one form or another. But the subtle things in the industrial automation space include things like a machine, which is an assembly of devices, a collection of devices that end up appearing as devices on the network. It's a subtle difference, but it was large enough to require that we put together our own kind of life cycle to make sure that we've covered off all of our requirements. One of the other things is a little different for if we looked when we looked at mobile phones is one of the big things with mobile phones is operators don't want devices connecting to networks that they don't control. So the manufacturer who's selling the device to a consumer, but then wants to restrict what can be done with that device. Again, that's completely outside of the scope of what we need for industrial automation. So that doesn't show up in our life cycles or our use cases at all. Now, one of the things that we absolutely had to have in order for this entire mechanism is a way to uniquely cryptographically identify every device. And there's a number of pieces that have to come together to make this happen. The first thing is there has to be some way of protecting the private keys that are kept in some sort of secure storage, like a TPM. TPM is one way of doing it. There are other mechanisms out there, other standards, but the expectation is vendors will figure out a way to protect their private keys. And once they have a way to protect their private keys, then they are able to issue what are called device identity certificates. Now, these certificates are defined by another specification, 802.1AR, and this is actually being used today by device vendors. They're actually putting these certificates onto the devices today, and so we're able to take advantage of this existing infrastructure and use it as a basis to build our provisioning model. And the one requirement that we've placed on this is that there has to be a product instance URI that uniquely identifies the device to all subsequent applications that are interacting with that device. And that identifier is an opaque string. The syntax is up to the vendor, but there are other standards. There's a DIN standard out there or the DID standard, 900. I can't remember the exact number, but it's a standard that some vendors are adopting in terms of telling them how to format their product instance URIs and provide the information. But from the perspective of everything else inside the device provisioning specification, it's just an opaque identifier. Now, one subtlety to sort of point out when you're dealing with the device is the device has an identity. The device is a physical object. It's a computer that's plugged into the network. It's got the protected storage. It's got firmware, and then on top of that, you'll have a bunch of different applications and the potentially multiple OPC UA applications. And each one of these applications has their own security configuration and their own identity. So your device will have its identity with the product instance URI, and then each application will have its own unique identity with something called an application instance URI. Now, with this model, okay, so we've got the device. It has its identity. You plug the device into the network. Some software can interrogate the device and get its identity, but that itself is not enough to determine whether or not that particular device can be trusted on a network. And there needs to be some other information that includes the CAs for the certificates that are installed on the device. Any other information about the device which may be relevant. The product instance URI obviously would have to be there. And so what the tickets are documents which exist independently of the device that are digitally signed by the manufacturer. And these documents include a timestamp and a globally trusted root CA that means that these documents could last a long time, perhaps last beyond the lifetime of the manufacturer. And that's one of the requirements we had to sort of think about, because a lot of times devices can last longer than the companies that made them. And owner operators need to be able to keep using these devices, and so we needed documents that describe them that would last, and hence the link back to these globally trusted root CAs. In terms of future directions, these are just ideas right now. We don't have any specific concept of where these particular things would be heading, but it's to give you an idea how we're constantly looking for opportunities to sort of enhance the OPC UA offering and make sure that it keeps up with technology as it moves forward. We don't want to be in 2030 trying to use 2010 technology. We want to be constantly improving, constantly moving forward. So by the time that we get to 2030, every UA application will be still using the state of the art. And in terms of the things that are coming down the pipe that will be relevant, well, always the biggest one is going to be quick in HTTP3, which is going through the final stages of release right now, and we're expecting that's going to become a significant player in the secure application, the IoT market moving forward, and we're going to have to figure out a strategy for dealing with that. That is about all I had to say on this topic.